Get started here.
If I don't get to work by 5:30, I can't get very
You just have to tell your supervisor, something to relate it to what you need to do, and then you say, okay, I need to learn this stuff. That's all you need. Let's go ahead and get started. We have some exciting stuff, exciting to me anyway, we'll go over today. Okay, we'll finish up arrays, and then we'll get started with structures. Okay, structs in C, which is basically related to classes in C++. Okay, so we're going to finish the whole class, with at least covering that portion. I'm hoping that we'll have enough material that we can go over the last homework assignment to be a BST implementation, a binary search tree implementation. You don't have to write a code. I'm going to write a code. You translate the code into assembly language. Okay. So the whole point is, how do we deal with structures in C, and so that you can write a program in assembly language, and it will still be compatible with C code that will deal with C structures. And we'll make it so that when you change a structure definition, the assembly code will be updated accordingly, so that you won't get a mismatch between the assembly code and the C code. Okay. So that's something that we'll try to cover between now and the end of the semester. And meanwhile, I'm really trying to grade the exam too. No, seriously. I spent more than 2 hours to grade one question from cisp310, not this class, and that was really time consuming. I think the partial credit thing has to go. Because I was looking at the output, the traces in cisp300, and I'm trying to give partial credit by looking at the trace versus what it's supposed to be, and then find out where it starts to deviate, and then go, okay, what can cause this answer to be wrong, and then just deduct points for that instead of saying, oh, this is wrong, 0 points. And that's what's taking so much time.
You can just give us A's.
I think there are campuses, within the Los Rios district that does that.
Which one?
I think you guys know which campus and which particular professor here. Alrighty. So let's deal with arrays. Okay. So let's write some code. I just want to show you where we are at this point, and also, one more thing. I did fix the link, just a little bit early in the lab. I forgot to re-upload the tar file, after I sent you the email. So now it is updated.
So that's why my make file wasn't working right.
Sorry?
Is that why my make file still wasn't working right?
It's not the make file. It has to do with two source code file has exactly the same name. So when the .o file is called for, it's up to the make utility program to go through its own list to say, oh, I need to make a factor.o file. How do I make one out of that? Okay. And it looks through the source file, and the first thing it found was .c.
Yeah, okay.
And it just says, okay, I now know how to do it. But no, I don't want to use .c. I want you to use .s. No, there's no way to convince the make utility program to go for the .s file instead of the .c file. So I fixed that by using a subdirectory for the .c version. And so this one is fixed. It does have the subdirectory, so it makes things a little bit easier.
And so it should work with r.s as is.
Correct.
Okay. Cool.
Yep. So the instruction that I included, which is what I sent earlier, that will work.
Just copy your .s file.
Yep, exactly. So you basically just make a copy first, so that you don't lose your stuff.
You got it to work.
So basically, this is. This is the instruction. If you have to turn in your, no, not this one, the one before that.
Can I just say that it's not C and got it to work?
Okay, so this one, basically includes the instructions, actual, command line commands to do it. So the first thing you do is you make a copy of your own, PADI subdirectory, and we'll rename it to PADI.original, and then you will copy the original tar file, to whatever, the original tar file. It's really just making a copy. I don't think you will need that, at this point. and then you download the new patty.tar.gz file from the homework assignment, and then you unzip that one, so you will have a brand new patty subdirectory with all the default files from my stuff. And then what you do is you just copy your own assembly version of the file to overwrite the one in the new patty subdirectory. So that way, you preserve the one file that you have to modify, but then everything else will be, compatible and work, because it has a C subdirectory for the C version. All right. So are there any questions?
You have a typo.
Hmm?
You have a typo.
Typo?
Yeah.
Where?
At mypatty.org instead of ORIG.
Oh, okay. Did you copy and paste it? But thanks for pointing out. Patty.org probably is a real website for hamburger patty or something. All right. So that's out of the way. We'll continue with
About a person named Patty.
What?
It's about a person named Patty, or like the Patty family.
Oh, interesting. I thought some meat company would have bought that domain name.
Oh, Patty family.
It's like Fries.com. For the longest time, Fries, the corporation could not get the website because there was one person whose name is actually Fry, and he got, was it Steven?
I don't know the new one.
Yeah, but there was a long story behind that too.
Same thing with O. Same thing with O.
What did you
Oprah
type
wanted
in?
to get that, but it belonged to a
What did
another
you type
company.
in?
Patty.org.
Interesting. All right,
Got
so
a
this
domain land page.
is sorry.
That doesn't look like the main landing page. Will you guys
Okay.
that?
All right, so where we left off last time was section 16.2.2. Okay, so now we can move on to indexing, because last time we kind of talked about how do we allocate enough space on the stack for the local variable. Oh, by the way, one more thing. When you are implementing the factoring program, you cannot use any .data section. So no statically allocated variables. It has to be allocated on the stack. Now the literal string can actually go into .text because we are not changing it. Okay, it's a const string, so you can actually move it into .text. So you don't need .data anywhere within that program. So just kind of keep that in mind.
Wait, what literal string?
Huh?
Literal.
When you use printf,
Yeah.
the double quote, I think is subtext, %d \n. That can go into .text instead of .data.
I guess what I was saying is, did you have to use printf? Because I just stole it from my last assignment and did this.
That'll be fine too.
Okay, cool.
Yep.
Yeah. Oh, I already asked this one.
I think you just went the longer way of
I
doing
copied
it.
and pasted it for my last program. So
Copy and paste.
Yeah.
All right.
Just modified it.
Okay, so let's go to indexing. This is our next topic. So the question is, how do we do indexing when you're doing it when you're doing everything in assembly language? So when you're doing indexing, if I skip the code, well, I guess I cannot skip the code here. The focus is right here. How do we calculate the address of an element in an array in general? Okay, so what you need to do is to think about how is an array implemented. Okay, last time we looked at how we allocate enough space for a local array in a subroutine. So the next question is, how do you think the elements within an array are organized? Okay, well basically they're all right next to each other. Okay, so that's why we have this little equation here. The address of b bracket I, close bracket, is b, the address of the entire array, plus I, which is the index, times the size of each item in the array. That's basically how you calculate the address of each item inside an array. So, so let's go ahead and look at the C subroutine, and then we'll go ahead and convert it into assembly. Back to here. Make a folder for today. All right, so let's go ahead and just write a particular subroutine in C that illustrates this particular concept. Okay, so we'll do something that is kind of meaningless. Okay, so we'll have in32t, which means every single item is a 32-bit signed integer. We'll call it array A. It has 32 elements, and then we have our index in32_t as I. I get 0, while I is less than 32, which is the size or number of elements in the array. We just say A bracket I gets the value of, I don't know, -I. Okay. So that's all we want to implement, but we want to do this in assembly.
You need to increment I too.
Oh, because otherwise it becomes an infinite loop. Okay, I guess I plus 1 or I plus plus, whichever way you want to specify that. Okay, so this is what we want to implement, and we'll do it in assembly. Does everybody understand what this is supposed to do in C? Because it's kind of pointless to talk about the assembly implementation if we don't understand what this is actually going to do in C. What is going to be the value of A bracket 30, close bracket, after the loop?
Negative 29.
Negative,
29.
no, negative 30. The value of an element is basically the negation of the negative side of its index. So A bracket, A open bracket 30 close bracket is going to have a value of negative 30. Right? Okay. So let's go ahead and see how we will implement this particular subroutine. This is the C version, and now we will switch to the assembly version. All right, so now we're dealing with the assembly version. Change the beginning of each line to a comment. And then we'll go ahead and do it. All right, so I will start with the usual thing, which is OEVP equals 0. There were a few questions asking, do I have to do this in my homework assignment? And the answer is no. Okay, I keep doing this, just to remind ourselves that the frame pointer EBP points to its own old value. So this way, we just keep reinforcing the concept of what the call frame actually looks like. But it absolutely is not necessary. The next thing is the return address. So once again, this is a definition that you don't really need because you don't have, we don't have parameters in this case. Okay, so there's nothing on the positive side of EBP that we really care about. But nonetheless, it is still kind of important. Okay, because in this case, you know what? I can actually show you how we can cause a stack corruption that can do certain things that's really nasty to those two particular items. Now in this case, we do have local variables, and the first local variable that we want to define is actually I, because A, typically has a lower address compared to I. So we'll allocate for I first. So I gets owed EBP minus the size of I. In this case, is 4 bytes, and then we have the array A, which is below I, and it has 32 items, and each one has 4 bytes. So this is how I would allocate for the local variables I and A. And then the last local variable is A, so that's the lowest address. It's the local variable with the lowest address on the stack. Are there any questions about these definitions? Now if you look at this, then you say, well, it seems like I can also be known as A bracket open bracket 32 because it's right after the end of the array. Is that making any sense? Okay, let me draw the picture on the whiteboard here. So the way it's set up right now is, okay, this is OEVP, old EVP, and the frame pointer EVP points to that. Okay, so that's why the offset is 0. It is, it has an offset of 0 from where EBP points to. 4 bytes above that is our return address, which is not pushed by the subroutine, it is actually pushed by the caller of the subroutine. And then we have I is right here. Okay, this is our I. It is 4 bytes below where EBP points to because it's a local variable. And then we have array A, which is 32 times 4, which is 128 bytes below that. So this is array A. Are we doing okay so far in terms of the layout of memory for this particular call frame? Okay. Now these 4 bytes here is also known as A bracket 0 because it's the first element of the entire array A. Is that okay? The next one, A bracket 1, A bracket 2, and so on. The last element of our array A is A bracket 31. Are we doing okay so far? What about A bracket 32? A bracket 33, A bracket 34. So if you do something about A bracket, open bracket 34, close bracket, it will affect the return address directly. Then you can have, now if you override it with just say, negative 34 because the bound checking of the loop was not set up correctly, it's the least of your worry because as soon as you try to return, bam, it will go to location negative something and you get a segmentation fault, and then the location of the segmentation fault will give you a hint of what went wrong.
Yeah, isn't there a way to like protect yourself from things on the stack, like make things constant or something? Or
Nope. The whole concept of const is a compiler thing. When you're implementing something in assembly, it completely bypasses the whole thing about const.
why don't they have like an instruction that prevents you from?
Because there's only one stack, and you cannot say certain portions of the stack is limited or off limit to somebody else. Because the whole thing is running in user mode, and you have control. Any part of your own program has write access to the
That's what I'm
entire
saying.
stack.
You can't alter anything else on the stack.
Yeah, you can.
Well, I mean, the operating system will just shut you down. So
You can modify anything on the stack as long as it's within the correct region in memory. Okay, from the operating system perspective, it just says, oh, okay, this is the entire chunk of memory. I think it's really big, like, I cannot remember the size of it, but it's really big. So it just says, I'm allocating this chunk of memory as the stack of your own program. And the operating system says, I would even be nice enough to initialize ESP to be here. That's all. Nothing prevents you from adjusting ESP all the way down here, or here, or here, or here. And nothing is preventing you from changing any location within the allocated stack.
is there a way to like ask the operating system how big your stack is?
I don't know exactly how to do it. I think it has to do with one of the /proc virtual files. So you might be able to adjust, how much stack is pre-allocated when your application starts to run. But even when it's allocating all this space, it's not like all of this is actually RAM because of virtual memory. So it's really paging in, the portion that you need. The rest of it may not even be loaded into your actual RAM. All right. So last local var is A in this case. But do you see the danger of doing it in this way when you exceed the boundary of an array that is a local variable? You start to eat into EBP and then also the return address. And this is actually how Stack Overflow exploits work. Does anyone know what is a Stack Overflow exploit or buffer overflow exploit? No? Okay, so we'll talk about that once we kind of get through this exercise. Okay, so last local variable is A in this case, and now we can define the entry point of init. As any subroutine, the first thing we do is push EBP, move ESP to EBP, so EBP becomes the frame pointer at that point. And then when we are getting out of the subroutine, we do exactly the opposite. We put ESP back into ESP, pop EBP, and then we perform a return. Okay, so I'm matching the entry code to the exit code right away so I don't forget. The allocation of local variables is done by just adding the displacement to the last local variable to ESP. That will basically allocate a chunk of memory and not initialize any single byte out of that chunk. This one is easy. Moving a 0 into I EBP, which is a local variable, we'll do it. This portion is easy too, so we'll handle all the easy ones first. Compare long 32 to variable I. If it is not less than JNL to end loop, end while. End while is a label, should be defined here. And then at the end of the loop, the body of the loop, we'll go back to the beginning of the while loop here. So the beginning is going to be here, just like that. So this way, I get the structure of the loop done already. We'll even handle this instruction first, because that's an easy one to deal with. Add L $1 to I EBP will increment the local variable I. So it's up to this instruction, and that's really the focus of this entire program, is how do we initialize a bracket, open bracket I, close bracket, which is an element in the array. There are several ways to do it, okay? There's a really fast and shortcut way to do it because we are dealing with a cisp architecture with some really kind of complicated addressing modes. But I don't want to do it that way, okay? I can do it, after we talk about this, the RISC or the reduced instruction set method first, and then we'll go back and talk about the cisp way of doing it because the Intel architecture makes it really easy. All right, I'm not too worried about the right-hand side because it's just the negation of I. So I'll leave that until later. Okay, I can do the computation, push the result on the stack, so later on I can use it. Okay, let's go ahead and do that. How do I calculate negative I in this particular example? You can multiply by -1, but that's kind of abusing negative multiplication. There's a quicker and easier way to do it.
Just set the most significant gesture to.
No, you cannot do that because it's a 2's complement, not a 1's complement. You put a 0 into a register and then you subtract I from that register and then you push the register on the stack. So that's, well, it's one way to do it. So you put a 0 into, let's say, EAX, and then you say subtract long I, the local variable I from EAX. So now EAX is negative I. Just push it on the stack, so we'll use it later. So when I do something like this, I'll just say push the right-hand side on the stack. So later on, I remember, what I just pushed on the stack. All right, so the right-hand side is done. Now we are going to deal with the left-hand side of the assignment. So as I talked about a little bit earlier, the address of any particular item in the array, let's say this is the I or element I in the array, is basically the address of A plus I times the size of each element. In this case, each element has 4 bytes. Okay. We'll do this in a long way. In other words, we'll do this in a way where if you have an array of structures, it will still work. Okay, because multiply by 4 is pretty easy. You can add I to itself twice. Okay, then you have the multiplication by 4 effect. But we'll do it the long way. So if you want to do it the long way, the first thing you have to do is to move I into one of the registers. Let's say EAX in this case. It's okay to reuse EAX because I pushed the result that I want to save anyway on the stack. So now EAX is free to be used again. And then we'll go ahead and use let's say EBX for the next one. So I want to multiply by 4, so I put 4 into EBX. And then we have the mul instruction using EBX. The mul instruction does not take an immediate operand, so that's why I cannot say mul $4. Or did I try it before? I think we tried it before and it did not work. Yep.
Shouldn't you move 0 to EDX?
No, because in a multiply instruction, EDX only stores the result of the most significant 32-bit, but it's not used initially to do anything. So EDX is not an incoming register, it's an outgoing register. It's only used to store the result, but it's not used, to specify the input and output.
Okay, so that goes for division as well?
No, division is different. In a division, the dividend itself is 64-bit, and that's why EDX is important, as an incoming, register. Now, technically speaking, I'm using the wrong instruction because when you do multiplication and also division, it is sign sensitive. In other words, I should have used imul, which is the signed version of multiply. But if I is not negative, then it doesn't make much of a difference. All right, so after this, I should have the product in EAX. Okay, so once I have the calculation done, what I have done is, after the mul, is this many bytes, or the number of bytes here between this point and the beginning of the array is now stored in EAX. What do I need to do next to this? After this, we have to add the address of A. Okay. So how do I add the address of A? Okay. Well, that seems to be one of the things that we have to do, and that's true. Okay. We do have to do that one step, but that's something else that we also have to do. Where's A? If A was statically allocated in the dot data section, that's all that I need to do. But not in this case because A is on the stack. So the symbol A is only representing the displacement or the offset from where EBP points to the first byte of array A. So there's one more thing I have to add in this case. EBP, exactly. So now we add EBP to EAX. And after all these instructions, what do I have in EAX? EAX is the address of A bracket I. Or if you prefer, you can also say that EAX is the address of A bracket I. In C, that's how you specify the address of A bracket I. Are we still doing okay so far? So now that we have the address of the element in register A, and then we have what we want to store on the stack, how do we do the final step in one single instruction? A pop L, which will retrieve something from the stack, but I'm going to put it into wherever EAX points to. Are we doing okay so far with this code? All right. That's pretty much it. That's array indexing in assembly language programming in general. Yep.
Could you do like $A parentheses EBP?
No, you cannot, because the dollar sign, or whenever you use the immediate operand, the value of the operand has to be determined when you're compiling or assembling or linking. It cannot be determined at runtime. But the value of EBP is runtime dependent, and that's why you cannot use a $A and then open paren EBP close paren. So that's why it has to be separated into two different steps. Good question. Any other questions?
Isn't this all the same as that one of the later operands, like the base and indirect?
Yes.
Isn't that?
So that's the other way to do it. Okay. So the other way to do something like this. Okay. So we'll just make this, call this alternative one. Let's see here. Okay. So this part I'll keep. Okay. So I'll just call this if long method. Do it this way. The add part I want to keep too. Okay, so here's else, and if, okay, so here's the short method. The short method is to use the based, scaled, indexed addressing mode. Okay, and that's basically one of those rare cases where, hey, that addressing mode actually makes sense and actually has applications. So if you want to do it that way, you have to designate one of the registers as a base register, but we already have a base register, don't we? Okay, our base register is EBP. So we have to designate another register as the index register, and we can just use EAX for that purpose. So I can move EBP into EAX, and I'll just comment here and say EAX is or will be my index register. And then I can finish up the rest with a pop instruction, and it will pop into a open paren EBP, EAX, and 4, and that's it. Because if you think about, where am I storing, in that pop out, that one single pop out instruction, it's doing all the calculations, but within, one single instruction, within the operand specification itself. So I don't have to spell out the multiplication, the adding of the offset, the adding of the base register, and so on. It's just done, within the operand itself. Do you guys still remember the based, scaled, indexed addressing mode? That's why it's there. Is it a whole lot faster compared to the alternative? Not really. I mean, it is faster, but not by a whole lot. Because what happens is, in this particular operand, internal to the processor, without having to fetch additional instructions, it still has to go through the same calculations. It's just that it doesn't have to go get the extra instructions, and therefore you're saving time because it doesn't have the extra fetch operation, in terms of accessing memory and try to figure out what to do next. But the actual time gain is not really all that much.
But naturally, RISC wouldn't have that, right?
A RISC processor would not have that sort of operand, so you still have to learn how to do it the long way when you're dealing with a RISC processor. Yep.
When doing calculations, does the processor move all of your registers into cache and then use the registers for calculations?
Registers are never cached, okay? Because registers by design can keep up with the ALU, all the time. What you're caching is memory content.
So how does the processor do different calculations and store extra?
Store extra.
Does it? I guess doing division.
Okay.
Or something. I don't know.
When you perform a division, you have the dividend stored in EAX and EDX. Okay, it's a 64-bit dividend. The operand specifies the divisor of the division. The calculation is all internal to the ALU. Okay, so when it's all done, then EAX stores the quotient and then EDX stores the remainder. So there's really no memory access unless the operand of the div-out instruction is a memory operand.
Okay, so it's just modifying the registers as it does the calculation.
I'm not 100% sure whether it's directly modifying the registers as it do the calculation, because the ALU has its own internal latches and registers, so it doesn't actually affect the register until the calculation is done. So I think it does not do the calculation using the registers. It only latches the result out, when the calculation is done. In other words, when you look at the ALU is typically represented as something like this with two inputs. So this input and this is the output. They are all related to registers. So these two can come from the registers, and this one can also go back to the registers. And the way it works is, at the beginning of the operation, the input will be latched. Okay, so you will read from the registers as the input, and then it will do the calculation. So during the calculation, it's not reading directly from the registers anymore, because the ALU has its own internal but very temporary storage. When it's all done, then you'll have the output basically specified here, and that's the time when the result is actually stored all the way back to the registers. So the registers are completely external to the ALU, but it's fast enough to keep up with the ALU operation. Okay. So are there any questions about this particular program? You know, how the short version works and why it is really equivalent to the longer version?
You're specifying a numeric constant for the size of the.
Because each 32-bit integer has
Right.
4 bytes.
But in the event of we're using a larger structure or something like that,
Then it won't work.
Like in C, we use size of to
Right.
get the.
Then it won't work because the operand in this case can only specify 1, 2, 4, and I think 8 is an option too. But that's all the options that you have.
Have like the size of type of.
Nope. The reason has to do with this particular portion, which is called a scale. The scale is actually specified within the instruction, the binary code of the instruction, using 2 bits. So using only 2 bits, you can only have 0, 1, 2, 3. 0 represents a scale of 1. 1 represents a scale of 2. 3 represents a scale of 4, and then 3 represents a scale of I think 8, and that's why I think it can go all the way up to 8. And that's why you cannot specify any arbitrary number, because the instruction, if you look at the binary code of the instruction, only 2 bits are allocated to specify the scale of of any addressing mode that involves the scale. All right. Any other questions about this code? No questions? Do you guys want to write a program that modifies the return address and see how weird things can happen? Yeah. All right. Well, now that we understand how how the stack is organized, we can actually craft programs to do stuff like that. So I'll just call this weird. But in this class, it's not weird anymore. Okay, so we have subroutine F, void, and this is the one that contains the local address. Local variable, which is an array. We'll just call this A, and it has only 1 element. So A bracket 1. I'm only allocating 1 single element here. So if you look at how the addressing is done, we only have A, so this becomes A. So this is A bracket 0, A bracket 1, and that's A bracket 2. So if I try to access A bracket 2, I should be accessing the return address directly. So we say A bracket 2. Let's see what we should do with it. Instead of putting some random value into it, which will cause it to crash and not very exciting, let's just do some arithmetics with it. Okay, I'm changing the return address to something a little bit earlier or later. Okay, in this case it's something earlier, and then we'll do it by, I think 5 will do it. Okay, so we'll subtract 5 from it, and now we have our main subroutine. And in the main subroutine, we only do one thing. Okay, we're just calling F, and then the main is going to return all by itself. sg.o weird.c. And for this program, to observe this program, how weird it is, you have to use GDB, because if you don't use GDB, then you cannot actually observe, how what kind of strange things it's going to do. So GDB weird, and we just say run. It's not coming back. Control C, it's like, why is it not coming back? Why do you think I picked 5 or negative 5?
Is it just calling main again and again? Because
It's not calling main.
It's calling F over and over again.
It's going back to the call instruction itself, because 5 is actually the number of bytes that the call instruction takes. Okay, so instead of returning to the instruction right after the call instruction, it's returning back to the call instruction itself and therefore it's calling the subroutine again. And when it returns, once again, it's returning to the wrong place, which is the call instruction, and that's why it is quote unquote an infinite. But it's not actually a loop, it's just you're doing it indefinitely.
Infinite recursion.
Hmm?
Infinite recursion.
It's kind of like recursion. It's not, well, it's not recursion because you're actually returning to the same point or the same address where the call instruction is. Yeah.
So what are the other 2 bytes in between?
Say again?
So what are the other 2 bytes in between?
The other 2 bytes.
Yeah, like if you have on the list, you have
Oh.
A0, OE.
Okay, A bracket 0 is really A bracket 0 because the array has 1 element. A bracket 1 is OEBP, and then A bracket 2 is the return address.
So what are the other 2 bytes?
What are the other 2 bytes?
2 bytes.
3 and
Yeah,
4.
Like you subtracted 5 and modified.
Right.
Yeah.
Well, the call instruction, the opcode takes up 1 byte, and then the other 4 bytes specifies the address of the subroutine that you're calling. And that's why the call instruction takes up 4 bytes.
The opcode?
The opcode, because the call instruction has 2 parts, right? The call instruction has one 8-bit thing, 1 byte specifying the actual opcode, out of 255, out of 256 combinations, one of those combinations is the call instruction itself. But after that 1 byte, you also have 4 bytes to specify the address of the subroutine that you're calling. And that's why together, it takes up 5 bytes. Not sure whether
4? You have 5 bytes there?
Yeah, there are 5 bytes here.
So wouldn't that be minus 8?
No, that's why it's minus 5. That's why I have
I think
sometimes minus 5.
Instruction is only 1 byte. Like add is 1 byte, move is 1 byte.
Yeah, all the popular or common opcodes, all the common instructions have only 1 byte as the opcode, so it doesn't need to take up as much memory to represent the instructions. The rarely used instructions can be longer because they're rarely used, so they can take up more bytes and not.
So could you like write that on the board, like the ordering?
Sure. Well, we can actually do this too. Since we turn on debugging, we can use object num. So obj dump. Okay. I'll do the other. Okay, so this will give me the object file, and we can do object dump. Obj dump weird.o, and we want to find out exactly what disassemble -d. Okay, so now you can see this is the call instruction right there. And this one is actually relative. E8 is a relative call. It's actually calling something that is relatively close to the point of where you're calling. But nonetheless, I'm not messing around with the instruction, the call instruction itself. I'm just messing around with the return address, which is a side effect of the instruction executing the call instruction. But that's why minus 5 works, because it makes it goes all the way back to the 89E5, which is our move ESP to DBP instruction. So every single time it's going to go take it back. The return address is supposed to be 19 to move on to the instruction next to the call instruction, but by doing a subtract 5 inside the subroutine F, I modify the return address to go back to 14, and therefore it's going back to the call instruction again, and it doesn't stop.
What is leave? What's the leave instruction?
Okay, which one? Oh,
Leave.
Leave is leave basically is a shorthand of the typical instruction that we use in this class.
2 lines.
Yeah, those 2
Oh,
lines
okay.
combined is basically leave, and you can probably expect enter, as the usual entry code of the subroutine. I don't want to use enter and leave, because I
Why
want
don't
to
they
expose
enter
the
there?
actual mechanism.
They didn't use enter there then.
I think it doesn't use enter because you can see in
Yeah.
subroutine F it uses the push and then the move instruction,
Yeah.
so it doesn't use the enter instruction. But there is an enter instruction to do exactly to do that too. Yeah.
I'm still a bit unclear on why a call is 5 bytes.
It's
It's broken down into 2 things, right?
Okay, it's broken down into, in this case, the actual opcode. E8 is the opcode. So 1110, 1000 as a big pattern is the opcode. Okay, so when the processor reads that instruction and decode it, it says, oh, I need to do a relative call. Okay. The other part, FC, FF, 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 specifies where I'm supposed to call, and I think that has to be fixed too. That is great because that really specifies -4. It specifies main plus 4. That's kind of strange. I think that the linker will fix it. Let me see if the executable file has, a better idea of what it's supposed to be. So, here we go. And we have to find main right here. There we go. Okay, so the linker does the actual calculation of where that thing is supposed to be, and it makes more sense now because it is actually specifying the address of something else. But it's a relative number. This is a negative number, so the call instruction, which is E8, in this case is a relative call, which means I'm only going to a place specified by the displacement from my current location. Because FFFFFE7 is a negative number, it's a very small negative number, where the magnitude is very small. It just kind of goes back to the entry point of subroutine.
All opcodes are 1 byte long.
Not all the opcodes. From here we can see the pop is 1 byte, but the move instruction is actually 2 bytes. The move instruction immediately before the highlighted code is move ESP to EDP, and that takes up 2 bytes. So 89 hexadecimal 89E5 specifies move ESP to EDP. But there are instructions, or there are many instructions that are only single byte. Like the push instruction is 1 single byte, the pop instruction is a single byte, the return instruction is a single byte.
So would that make it possible to have the operating system, I guess, read your own opcode by modifying the stack?
You cannot execute code that is in the stack, and that's how the execution inhibit bit works in modern processors. So basically, we don't want to execute code from the stack because that's an imitation of stack overflow exploits. Well, do you guys want to talk a little bit about stack overflow exploits, because we are actually pretty much at that point where it is relevant to talk about that. Okay, so let's talk about stack overflow exploits. Okay, so stack overflow exploits usually start with code that looks like this. So I'm gonna do a exploit.c. Okay, so let's say you have a subroutine that deals with the parsing of one particular section of a TCP/IP packet, okay, of some kind of protocol. Okay. Can be JPEG, okay, anything that has a standard. So we'll just call this, parse something, and you'll be given a pointer. Okay, well, we can make it a char pointer or something, whatever, it doesn't matter. So we have a little char pointer to the packet, whatever packet you're supposed to process. And in here, as one of the requirements, you have to have a local buffer of some kind to store, whatever you're processing, whatever this subroutine needs to process. So we have, char local buffer. We'll just say that. Okay, now this is the important part. The important part is a programmer reads specification, and the specification says, oh, you know what? The description field of a JPEG file can only have up to 256 characters. Okay, so as a programmer, okay, with no malicious intent, you just go, oh, okay, so I need to allocate 256, or if including the null terminator, maybe 257 bytes. Okay. All right. So this is the one of the biggest mistakes that most people make is, oh, you know what? The file that I'm processing is playing by the rules. Because it may or it may not play by the rules. What if it is not playing by the rules and it has more than 256 characters? Well, let's see what happens next. Okay, so we have ... here, and then at some point you find out exactly where in the packet starts the description, and you want to put it into your local buffer for some further processing. And this is the second mistake. This is really, really a common thing that people do, and it's really bad. So you have a string copy in C, and string copy takes the destination as the first argument, and packet or the source, as the second, argument. And maybe at this point you know the offset to packet, so you will say, packet plus description start. Okay, doesn't matter what it is. So this is a typical C subroutine, or C way of copying something to a local buffer. But there's no length limitation. Okay, string copy by itself is only null terminated. In other words, if the file is malformed so that that particular section actually has, let's say, 500 bytes before there's a null terminator, this particular subroutine call will copy 500 bytes to local buff. What happens on the stack? It's local buff. This is the last byte of the buffer itself. It will just wipe out some other things on the stack. Okay? So let's take a look at the stack at this point. So we have the stack here. So we have a stack here. We have local buff all the way down here. Local buff is all the way down here because one, it is a local variable. Local buff has 257 characters, 256, whatever you want to call that is fine, okay? But it does have this much storage. Above that would be some of your other local variables, and then above that would be your OEDP. Above that would be your return address, and whatever is beyond that would be owned by the caller of this subroutine. Okay, this is not stuff that this particular subroutine specifies, but the caller of the subroutine specifies. Are we doing okay so far with the layout of the callback? Okay. So with an instruction or with a statement like that, calling the string copy, but without actually limiting it to only copy up to 257 bytes, and this can copy a lot more bytes. So this particular string copy will basically overwrite a whole bunch of bytes beyond the end of the actual array local buff. Okay? Are we still doing okay so far? Now, it does two really nasty things because one, it overwrites the return address with something new. Okay? And then it also overwrites some other portion on the stack. So the craft of Stack Overflow exploit is what do I need to overwrite this portion so that when at the end of this subroutine, when it does execute the return instruction, I want that return instruction to return to some portion here, stuff that I just freshly overwrote on the stack that contains the exploit code itself. Are we doing okay so far? Now it cannot be very precise. Okay, it cannot be precise, and that's why with a Stack Overflow thing, usually it has what we call a sled, SLED, a sled. Basically, it's a sequence of single byte instructions, like a no-op instruction. So if you land anywhere within the sled, it will eventually slide all the way down to the actual payload of the exploit. So it doesn't have to be exactly to the instruction. At the beginning part of the exploit, it can be, you can have a long sled, right? You can have a sled of 1 kilobyte. So if it lands on any one single byte of that 1 kilobyte, you're still good. So the really crafty part is how do I what should I overwrite, with the return address so that I can land, on, some place on the sled. Yep.
Isn't it a lot of guesswork or trial and error then?
If you have a debugger, it's not really that much of a problem. Because you can, actually, monitor how the stack is used, during the execution of whatever program you're trying to play.
But I mentioned like whoever's doing the exploit probably doesn't have the source code to work with to begin with. He's just kind of guessing, there's probably these kind of weaknesses that the programmer is getting.
That is correct. But you can still look at, what you can do is you still have tools that can, stop, the execution of whatever program you're trying to hack into, you can stop the execution of that program at any time. And then you can look into the stack and look at the stack pointer and then try to trace what it is, what is the content of the stack at that point. So they have to do some groundwork to figure out, what they should overwrite here. But that's really the really critical step is this part here. And crafting whatever packet that is now formed is the other part.
It seems really tedious.
Not really tedious, because what they do is they just create a packet that is overflowing to basically just randomly trash the return address. Now what happens when you have a randomly trashed return address? It just goes right with a segmentation fault. But when you stop in the segmentation fault and you get a core dump, then you have the entire memory layout at that point, including the instruction pointer at that point. Am I making any sense?
Oh yeah.
So with the instruction pointer at that point, and then you have the actual executable on the other hand, you can match it, and say, oh, okay, so this is where the crash happens. Okay, then you can look and disassemble the code and find out, okay, who can possibly call this instruction? And from there, we can actually try to track down, the approximate address of the stack pointer when something like this happens. In fact, the core dump will tell you what is the stack pointer at that point. Because it is doing core dump only because the return address is wrong, but ESP is preserved in the core dump, or in GDB, you can actually ESP at that point. So now you know exactly what ESP was at this point. So your return address only has to be somewhere close to the stack pointer to return to one of these other overwritten locations.
And then within there, it basically loads up executes the payload that you wanted.
Yeah, usually the payload is very simple. It opens up a shell and does a little do a connection to the outside, and that's all. Because that's basically what you need to break through a firewall. Because a firewall only blocks incoming traffic, but normally it does not block outgoing traffic. So if you open up a port and just say, just call back mothership, using a very simple protocol, that just opens up the floodgate, for further invasion. And typically what they do is they want to locate a section of code like this when it is executing with elevated privileges. So in Linux, it will be a program that has what we call SUID, set user ID to root privilege. In Windows, I think they have equivalent mechanisms. So certain programs are already running with root and elevated privileges. And when an exploit like this happens, then the exploit code will also be executed with elevated privileges, and then it can basically do anything it wants. There's no stopping it. Yep.
How does the processor know that those 4 bytes are the return address?
Because at the end of the subroutine, the stack pointer will be pointed here, right before the RDT instruction, the return instruction.
Yeah, but how does it know that the next 4 bytes that it reads is going to be the return address?
That's how the return instruction works. The return instruction basically said, whatever the stack pointer points to, I'm going to use it as my return address. And if you have a normal subroutine, then by the end of the subroutine, the return instruction, or by the time you execute the return instruction, the stack pointer will be pointing here.
Okay, yeah, I get it.
So by talking about this, I'm probably violating 20 different codes in the DMCA and a whole bunch of other rules, international rules and whatnot, laws, whatever. It's not specific to a particular product, so it's actually okay. If I were to talk about this within the context of a particular program that has copy protection mechanism or whatnot, then I'll be in big trouble. But just talking about the general mechanism that actually does not work on most modern architectures anymore, it's okay.
You're teaching defensive programming.
Exactly. Why it is a bad idea to use string copy. The defense is very simple. You just add and to it. String and copy, and you specify only copy up to this many bytes. And that's already much better than what it is now.
So what if they have strict copy? Like,
It's convenient.
Because we trust people. We trust that all the strings are properly formed, and whatever the boundary is properly respected. But that's how exploits work. Some of the exploits. So, are there any questions? Isn't that fun? I mean, that's kind of fun stuff. You can write your own program and try to break it. Yep.
So how would you insert your malicious code into the program?
How do you insert the malicious code into your program?
Into the program, yeah.
Push your code on the stack.
Well,
You-
let's
you
take a
just
look.
push it on the stack then.
That's not an excuse.
Well, if it is your own program, you
Yeah.
don't have to hack your own program because you know exactly what
If
it's
it's-
doing,
if
right?
it's someone else.
Okay, so what you do, in this case, okay, in this picture, your payload is going to be here, right?
Yeah.
That's basically your
How do you put your
payload.
payload in there?
Sorry?
How do you put your payload in there?
It will be a part of, let's say, a description of a JPEG file or a GIF file. Because in a GIF file, they have a designated area to specify, like comments and whatnot, but it has a certain size of certain limitations to the size of it. So you're counting on sloppy programming on the part of whoever wrote the code to deal with, JPEG or PNG or GIF files. And so you just randomly pick a standard that has a particular size limit, and you say, I'm going to make something that will break it. Okay. If a string copy is actually just if a strict string copy was implemented, and then you see if it crashes the program. If it does, then you have just found something that can be used as an exploit. If the program doesn't crash and just comes back and say, oh, this file is no good, then you cannot, it doesn't work with that particular program. This is actually one of the flaws of the GDI DLL in Windows. So there was one time in the history of Windows where if you go take a look at one picture, your computer can end up getting infected. Nobody remembers that? Let's look it up. I mean, this is really important stuff. This is actually why we need to take a class like this, is to really understand the mechanism of stuff like this, so that we can avoid certain types of programming mistakes. Okay, so you just look up GDI Windows exploit, and right there, security bulletin critical. An attacker who successfully exploited this could take blah 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 blah. Okay, so this is back in 2008, which was only 5 years ago. So let's read the text a little bit here, just to understand the severity of this particular problem. The security update resolved 2 privately reported vulnerability in the GDI, and the GDI is used in just about any type of graphics or bitmap rendering in Windows. So if in Internet Explorer, you can go to eBay, look at a picture of something that you buy, or potentially you want to buy, let's say a laptop computer. If the GIF itself is malformed, and containing this malicious code, just looking at the picture can get your system, hacked basically. Now, it's bad enough the way it is, but if you remember in Windows, if you use any home edition of Windows, the default user is running as administrator. So the exploit will also run, guess what, as administrator. And now it can basically do whatever he wants. Now, the same thing can potentially happen, let's say in Linux. But if you're using like a default user account and it's going through the browser, yes, the exploit can basically kill and get all the stuff that you own as an end user. But it won't have the permission in order to hack the entire system as a whole. So the damage is still there, but it is limited. But when you do something like this in Windows, especially a home edition, then you can completely host the entire system.
Is it in Linux, even if you're a super user, if your malicious code gets a hold of higher SUID, can you just use something like mandatory access
Yes.
controls to prevent super
But your
users?
browser is not running as as SUID process. So so this kind of exploit cannot get into anything that's really serious But potentially, if you can identify one of the SUID processes and hack it, then yes, even in Linux, you can hack in and do bad stuff as root.
But I mean, like, you could limit a lot of damage if you have like really strict, like if you use something like app armor or like memory access controls where you like limit super user actions.
Yeah. Yep. Basically, you want to not use SUID at all. So as if you have as few processes running as root, the better. Because the exposure is going to be smaller. It's not like the other programs are bulletproof. It's just that if those other programs were hacked, it doesn't cause damage to the entire system. It just causes localized damage. Because when you run something that's root, you can easily install rootkit. And once you have a rootkit installed, the virus scanner is useless because the rootkit will basically completely shield anything that is malicious. So when you do an ls or ps, or basically commands to list files and processes, a system that has a rootkit installed can basically hide those processes and files and just say, they never existed. There's no such file. Just ask Sony. Sony. Yeah, Sony, put a rootkit to computers, way back, I don't remember the year. But when you put an audio CD to play on the computer, it will silently install a rootkit, so that they can monitor what you're doing with that CD. Yeah, go ahead.
Have you successfully used this exploit?
No. But this is, I think these exploits don't really work anymore.
Have you tried?
No.
I don't think you'll like that. Doing that.
Oh, somebody got into big trouble, really hot water that time. Not that, they stopped it in any way to do other things that are nasty later on. Yep.
Yeah, we've had to protect against that with HTML and server-side information being portrayed over HTML pages. Like if you have a form and they insert like malicious JavaScript in the form and then hit submit, your server will run it just automatically if you don't have the right server-side protection.
Now the server side does not run JavaScript
Well, it
code.
depends if it's written in JavaScript.
That's why you convert.
Even if you
greater
convert to
than
copy.
symbols, ampersands, all that.
No, the ampersands are what catch you. You display server-side information using equal ampersand or equal add.
But that's a different level,
But there's also-
because at that level you have SQL injection and all kinds of other things they can do with a server. In fact, most of the exploits now are not exploits like these. They're mostly exploits of web scripts, PHP scripts and stuff like that. So when people are not careful and they directly put a parameter in a URL into a query, then you can append additional stuff in the URL or in the query that will basically dump the entire database out instead of the few entries that it's supposed to retrieve. Yep. That's a very common thing, and I think a lot of that comes from PHP programming for dummies, or the idiot's guide to PHP programming. People just copy and pasted code a long time ago. But that has nothing to do with assembly language programming, but this does. Yep. So really, really bad things can happen with this type of exploit. Are there any questions about this? Does it make sense to you that something like this can happen? Okay. And without the understanding of assembly language programming, it's pretty it's not easy to kind of grasp the concept of this kind of exploit or how it can be done. All right. Yep.
How do you guard against it?
How do you guard against it? You turn on, well, these days it's pretty easy. You turn on the execution from in image bit of the processor. So basically, it won't execute any code that is not designated as basically our .text. So double check and confirm that.
It can't execute from the stack.
Yeah, exactly. Because the stack is not designated as a section of code that can execute. So I think it's called execution in init.
Return outside of execution.
Response. No, that's not it.
Good luck.
Yeah, I know. That'd be like
Is it execute or execute in init? There we go.
If you could, I'm not saying that you could calculate or something.
And we'll just look up Intel.
Find some base based on where it puts a node and something. Finite matters.
Does anyone know the actual name of that particular
Is it the bit level? I think.
huh?
I think it's like bit level function. I think.
Bit level?
Is the Intel processor rings or something?
No, it's okay. In stop execute code in stack. There we go. Okay, a stack overflow known as stack smashing occurs the second attempt to prevent the execution of malicious code. Okay, so this might have it.
Not executable stack. Protection schemes.
Protection schemes.
Stack canary.
Stack canary, named after the analogy used to detect a stack of before execution of malicious code can happen by placing a small integer in memory just before the stack return pointer.
So this slide would wipe it out.
Non-executable stack, that's data execution prevention. Okay, that's it. And it's a feature of a processor. You can enable that feature, so you know it won't execute code in the stack that is placed in the stack itself.
You know, it's kind of annoying is sometimes like I had to do tech support for Symantec one time, and they wanted me to disable data execution prevention so that they could go in and troubleshoot their product. And I found that quite annoying because you're basically giving them the keys to your car or your computer in that case.
Yep, pretty much. Because you know, Stack Overflow exploits are very easy to write, and there are many programs with existing security holes around this. And I think this feature is actually in the Intel processors too. So notable worms, notable examples: the Morris worm, the Witty worm, Slammer worm. Does everybody understand how a worm is different from a virus? No? Okay, in biology, what is the difference between a worm and a virus?
Self-replication. Entire organism.
Well, they can all replicate, but one can seek out and destroy, and then the other one is just waiting there, more like a Trojan. It's like, okay, I'm just waiting for the right time to replicate. Someone has to activate me. So a virus requires activation. A worm is autonomous. So a worm, once you get a worm infected on a particular machine, it can actively seek out, to other machines on the same, network or other networks, and say, okay, I'm probing this IP address, I'm probing this IP address, I'm probing this IP address to try to, send itself, or copies of itself out. A virus, is dormant until you activate it, until somebody clicks on the link or clicks on the executable, then it's activated. Okay. So are there any questions about, all the stuff that we talked about today? No questions? I think this will be interesting, I will give you a program in the source code that has a string copy with no protection of, how many bytes it's going to overwrite. And then you guys will have to hijack it and say, okay, just give me, hello world, okay? When I run that program using a particular input file, your input file, then it will do something it's not supposed to. I think that'll be interesting. I'll give you the source code. I mean, once you have the source code, it's a whole lot easier because you can put a breakpoint and find out exactly where the stack pointer is when the program gets to that point. So it just basically makes it a little bit easier. I think that would be a worthwhile homework assignment. Yep. Okay. So that will be the next homework assignment. I'll give you guys, that on Thursday. Yes, because to start with bash shell is really just a few bytes of instructions. So then we really easy. I think it's just more. Just look at the services. I think Swarm is a very easy one because there is one catch, when you write exploit code, is your code, the exploit code, cannot contain the byte 0 itself. Because the byte 0 itself is the null terminator, so string copy will only copy up to the first null byte in the sequence. So you will have to write your entire code avoid using 0, 0 as a byte within your exploit payload. So that really is a kind of a challenge which makes assembly language programming kind of interesting and necessary, because if you leave it up to a C compiler, yeah, it will crank up all kinds of code containing the 0 byte. So your entire exploit will only load up to a certain point, but it won't load completely. So you have to craft your own program so it avoids the use of 0 itself. Yep. So now you're armed and dangerous. All right, I'll see you guys on Thursday. And don't forget the homework assignment is due on Wednesday. I mean Thursday.
Hey, Will.